Chapter 9 is about proofs, and we're going to be looking at proofs by induction today. And we're going to start out by just looking at conjectures. We want to finish this conjecture. We want to make a claim. The sum of the first n numbers is what? So what we can start by doing is plugging in numbers and seeing what we get. The sum of the first one numbers is 1. The sum of the first two numbers is 3. Sum of the first 3 4. And what we're trying to do is look for a pattern here. And the pattern that we can figure out is that this is n divided by 2 times 1 plus n. For n being an element of the positive integers. This is a conjecture, it's unproven. We're going to give a direct proof for this, meaning we're going to prove it algebraically using theorems and things that we already know. So what we're looking at is 1 plus 2 plus 3 plus ... plus n. We're trying to show that that is n divided by 2 times 1 plus n. One way to prove this is by recognizing that this is an arithmetic sequence. And we know that the sum for an arithmetic sequence is given by that formula. D is 1. That's how we know it's arithmetic. We're adding up n terms, so that means that a sub n is equal to n here. And a sub 1, the first term, is equal to 1. So now we can just plug this stuff in and get n divided by 2 times 1 plus n. We've just proved, because this is an arithmetic series, that the sum for this particular arithmetic series, the sum of the first n integers, is n divided by 2 times 1 plus n. That is a direct proof. Induction is a little different. We're going to make another conjecture here, just to practice. I want you guys to try to fill in the blanks if you're watching this. Pause it if you haven't done this yet. But the conjecture would be, and there's actually any number of them, but one conjecture would be that 11 to the n minus 1 is divisible by 10 for n that's an element of the positive integers. Or some of you might have seen that it was divisible by 2 or maybe by 5. This is an unproven conjecture. Induction. Suppose a proposition is called P sub n, which is defined for every integer n that's greater than a, where a is some element in the integers. Now if P sub a is true, that smallest value, and we're able to show that P sub k plus 1 is true whenever P sub k is true, then our proposition is true for all values of n greater than a. So what does that mean? What that means is that if A is 1, if P sub 1 is true, then P sub 2 is true. And if P sub 2 is true, then P sub 3 is true. And so on and so on and so on. If we've shown that in general K plus 1 is true and K is true, we've shown that everything after 1 is also true. And the process that we're going to go through is that we're going to show the principle is true for the first value. Then we're going to assume that the principle is true in general, and we're going to use the parameter K. The thing we're then going to have to do is show that the principle is true for the next term, for K plus 1. So we want to prove the sum formula for a geometric series by induction. So this is what we're trying to prove. First thing we do, this is our proposition. This is P sub n. Show P sub 1 is true. And I guess I left something out here. This property is true when n is an element of the positive integers. And that does make a difference. So the smallest positive integer is 1. So we're going to show P sub 1 is true. So that means A sub 1, that's the left side of this, is equal to A sub 1 minus r to the first over 1 minus r. Those cancel. A sub 1 equals A sub 1. So P1 is true. Now we're going to assume Pn is true. But we're going to plug in the parameter K. So this becomes A sub 1 plus A sub 1 r plus yada 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 A sub 1 r to the K minus 1. We're going to assume that this is equal to A sub 1 times 1 minus r to the K over 1 minus r. Now our task becomes show P sub K plus 1 is true. If we're going to show that's true, what we're looking at is A sub 1 plus A sub 1 r plus yada 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 plus A1 r to the K minus 1 plus one more term. And that would be A1 r to the K. We want to see if that fits with this rule. We want to know if this is equal to A1 times 1 minus r to the K plus 1 over 1 minus r. We want to take the left side here and use our assumption to show that this is true. All of this stuff, we assume that that is equal to A1 times 1 minus r to the K over 1 minus r. Now we can factor out A sub 1. And we're going to need a common denominator in here. of 1 minus r. Now we distribute and combine into one fraction. We get the r to the k plus 1 because we're taking r to the k times r to the first. We have to add the exponents together. There's really a 1 up here, remember. And now those cancel, leaving us with a1 times 1 minus r to the k plus 1 over 1 minus r. So we just showed that k sub 1 is true. So what we say now is, since p1 was true, and since pk plus 1 is true, when p sub k is true, we know our proposition is true by mathematical induction. And that's how you need to end all of these problems. You need to conclude it and say that you used math induction to do the proof. They're all going to be worded fairly similar at the end. So we want to prove this. I'm going to write this out for my claim, for my proposition. One squared plus 2 squared plus yada 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 plus n squared. We're claiming that that's equal to n times n plus 1 times 2n plus 1 all over 6. And the first step for math induction is to show p sub 1 is true. So 1 equals 1. Therefore, p sub 1 is true. The next step is to make our assumption. We're going to assume p sub k is true, which would say that 1 squared plus 2 squared plus yada 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 plus k squared, we're saying that that's assumed to be equal to k times k plus 1 times 2k plus 1 all over 6. And now we need to show pk plus 1 is true, which written out would be 1 squared plus 2 squared plus yada 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 plus k squared plus k plus 1 squared. We're trying to show that that is equal to k plus 1 times k plus 2. I'm putting k plus 1s wherever there's a k. 2k plus 3 all divided by 6. That's our task. And we're going to recognize that the first part of this series is what we're assuming to be true. So we can say that that is k times k plus 1 times 2k plus 1 divided by 6, but it's still being added to k plus 1 squared. We'll need a common denominator.
We have a couple quick announcements. Park singers will have choreography tomorrow morning from 6:30 a.m. to 7:30 a.m. in the choir room. Any questions? Please see Mr. Wiskowski. Again, Park singers choreography tomorrow.
And now, essentially, we have two terms, and one way we could go about this.
JV's girls soccer bus will leave promptly at 3:50.
If we think about this as having two terms, each of these terms have a k plus 1 in them. So I'm going to factor that out, and I'm left with k times 2k plus 1 plus 6 times k plus 1. And now I'm just going to expand out. And then this is factorable into k plus 2 times 2k plus 3. And this is over 6, which is what we were trying to show. So since P1 is true, and pk plus 1 is true when p sub k is true, we know p sub n is true for n being an element of the positive integers by math induction. This example you can read about in the book if you like. If you want me to go through it with you, just feel free to come in and ask. I will go through this example, prove that this is true for all n in the positive integers, or where n is in the integers, but also that n is greater than or equal to 0. So essentially this is the positive integers with 0 included. So our claim is this, and we're going to show p sub 1 is true. So 4 to the first plus 2, I lied. We shouldn't be showing p sub 1. We should be showing p sub 0 in this case, because 0 is the first value that we use. So 1 plus 2, that's equal to 3, and 3 is divisible by 3. So we've shown it's true for that first value. Now we're going to assume 4 to the k plus 2 is divisible by 3.
Just a reminder to staff to please stop in the staff lounge on your way to conferences. Thank you.
And now we need to show 4 to the k plus 1 plus 2 is divisible by 3. By making the assumption that 4 to the k plus 2 is divisible by 3, that means that 4 to the k plus 2 is equal to 3 times some value where a is an element of the integers. That's what it means to be divisible by 3. So now we got to do a little bit of work. 4 to the k times 4 plus 2. Our goal is to be able to write this as 3 times some integer. And we know that 4 to the k is equal to 3a minus 2. I'm using the assumption from above to substitute in here. And this is equal to 12a minus 8 plus 2, and that's going to be 3 times 4a plus 2, sorry, minus 2. So we've just shown that 4 to the k plus 1 plus 2 can be written as a multiple of 3. So since 4 to the k plus 1 plus 2 equals 3 times 4a plus 2, it is divisible by 3. And now, since P1 is true and PK plus 1 is true, when P sub k is true, our claim, I'll write it out this time, 4 to the n plus 2 it's true by math induction.